Okay, so if we're in the business of constructing more efficient estimators, we're going to go to all the trouble of doing it, we ought to be able to test for the presence of heteroscedasticity. Oh, let me draw a little graph for you, by the way. Maybe will help us understand what's going on. Regression analysis, as we've been discussing it, is all about conditional means. What's the mean of y conditional on x? And the traditional interpretation is that there is a regression line that looks like that. And conditional on a given value of x, there's a distribution over the possible values that can be taken by y. And if we move to a different x, conditional on x2, there's a distribution of the possible values for y. Same for x3. And if my artistry was any good, the variance of each of those density functions would be the same. And that's what we assume in garden variety regression analysis. What we're just talking about now is the following proposition. I have the same data on x and y, but this time the scalar diagonal error covariance matrix assumption has been violated. Now it turns out that when x1 is very small, when x takes a very small number, same regression line, by the way, when x takes a very small value, the variance is quite small. When x is taking kind of intermediate values, the variance is a little bigger. And when x takes a really big number, the variance is really big. So on the picture on the left, the error term is homoscedastic, and the picture on the right, the error term is heteroscedastic. Okay? So we have data on 3 food trucks at Temple, where we're modeling some kind of behavior at the food truck. And so the disturbance term is homoscedastic, because we're just talking about food trucks at Temple University. And they don't vary much. The data is very tight for all these food trucks, because they all employ at most 2 or 3 people. They're all about the same size. They all see the same client base, and so on and so forth. On the other hand, in another study we're doing, we have data on Rhode Island, which is a pretty small state. And their consumption of high fructose corn syrup is not going to vary much year to year, because there aren't too many people there to eat it. Indiana is kind of an intermediate-sized state, and so the variance of consumption of high fructose corn syrup is a little greater than it was for Rhode Island, if for no other reason than the fact that Indiana has more people to live in. There are more people to suck down that high fructose corn syrup. And then you go to Texas. You go to Texas, that's a big state, a lot of population, a lot of people sucking down their high fructose corn syrup drinks. And so the variance of fructose consumption is quite large. So that would be a heteroscedasticity example. There's a lot of heterogeneity amongst the primary sampling unit when we're looking across the different states. When we're just looking at food trucks at Temple, that's a pretty homogeneous group. X is an independent variable. X1 is a small observation on X. X2 is a little bit bigger observation on X, and X3 is a big. Yeah. X is just one variable. And the subscript is just an index number for the observation on that variable. Okay. So we already know that if this is this is a scalar, a non-scalar diagonal error covariance matrix. The disturbance between terms doesn't have any correlation. So the off diagonals are still 0, but the main diagonal is no longer scalar. So we already know that ordinary garden variety least squares is not efficient. There is a more efficient estimator. So we want to test to see whether or not heteroscedasticity exists in our data. So the scheme suggested by Goldfeld and Quandt, which is still in use 50 years later, is to divide your sample into 2 parts. In one part you put all the small states, and in the other part you put the big states, and you estimate a sigma squared from the little states, and you estimate a sigma squared from the big states, and if the data is homoscedastic, your estimate of sigma squared ought to be the same in both parts of the sample. And so that's your estimate, the ratio of those 2 variants. Choose a column of x according to which the error variance might be ordered from smallest to largest. So in our example with states and high fructose corn syrup consumption, we could order the data by population, from the smallest states to the biggest states. And arrange the observations in a model in accordance with the size of xj population, say. Omit an arbitrary number of central observations. The reason for doing that is, suppose that I just picked, these are 3 particular observations out of x. There are really 120 of them here, but I just showed you 3. And suppose it's the case that as x is increasing, the error variance is increasing, but only very slowly. So when I show you the observation when x is really small, the variance is obviously much smaller from the one where x is very large at x3. So it's easy to see the difference. But suppose I were to draw the one, I were to pick an x very close to x2 below it, and another x that was a little bigger than x2. And I would look at the error variance in those two instances. Well, those would be almost the same. So by dividing our sample in two parts and taking a piece out of the middle, we make sure that we get a bunch of observations down here where the error variances are small, and we get a bunch of observations up here where the error variances are big, and no meeting in the middle. And we construct a net statistic. We take the residual sum of squares from the small end of the sample and the residual sum of squares from the big end of the sample. And under the null hypothesis of homoscedasticity, the two residual sums of squares should be the same. If it's homoscedastic, I should be able to estimate the error variance out of either part of the sample, or it should be the same. So then I construct that ratio of residual sums of squares, and if I was clever enough to make sure that I had the same number of observations in each half, I don't have to worry about the degree of freedom.
Do we need to do this for all degrees? Or if we have a multi-regression, say x, there's heteroscedasticity with that, but homoscedasticity with the other independent.
Oh, I guess one of the things, again, that's part of the art. And what's a trellis? Anybody know anybody a gardener and know what a trellis is? Know it? Yeah. R, and I'm not so sure, but I believe it's in SAS also, allow you to create what are called trellis graphs. As Frank said, it's kind of a grid. And the trellis graph looks as follows. For the sake of argument, let's suppose that we just have y and x as two variables. So we have a dependent variable and a single independent variable. A trellis graph says, let's plot y against itself. And so when y is plotted against itself, your data points just look like that. So that's not a very interesting plot to look at. When you plot x against itself, it looks like that. When you plot x against y, x is now measured on the vertical and y is measured on the horizontal. Now you potentially have a very interesting scattergram. And suppose that your y is on the horizontal. Suppose that your scattergram, suppose that's the way your scattergram looks. I put the thing on the long axis. Conditional on x, up here, the variance in y is very small. Here, the variance in y is quite large. So by cleverly doing some plots, you can infer, even before you do the statistical tests, whether or not heteroscedasticity is in your data. Here's the reason I did this. Suppose that you had x1 and x2. Nick's question was, how do I know? So these main diagonal boxes are always empty in this plot, x1, x2. So now, for example, in this cell, you get a scattergram that shows the relationship between x1 and x2. In this cell, we saw the relationship between x1 and y. In this cell, we could look at the relationship between x2 and y. So in this case, it might look like that. That looks pretty homoscedastic. As we change the values of x2, the spread in y doesn't change very much. So I might look at that trellis graph and say, oh, clearly I have a collinearity problem, and that's evidenced by what I see here. And for some reason, the error variance seems to depend in some way on x1. So I would use x1 as a variable by which I rescale my data. And that would, by rescaling the data then, you could make both panels look homoscedastic.